Hello, this is Dean Waldo. I'm from Pacific Lutheran University, and I'll be showing you a multi-step example of a kinetic reaction. So this will be the reaction of two N2O5 molecules to produce 4 NO2s plus 1 oxygen. And what I'd like to just point out first is that we are given a mechanism, and we're given a 4-step mechanism for this multi-step reaction. And let's just look at what we typically do when we're solving these multi-step reactions. Step 1 is to look at the mechanism or propose a mechanism. Here we're given one in 4 steps. So the first one is the decomposition of N2O5, and we'll call that Ka going to NO2 and NO3. It has a corresponding rate law for what we'll assume for all of these cases is an elementary reaction, hence the rate law, in this case first order in N2O5. The second step is an NO2 plus NO3 going to produce the reactant again. So in other words, somewhat like a pre-equilibrium step. This rate constant will be Ka prime, indicating the backwards direction of that reaction. And in this case, it'll be a second order overall reaction with NO2 to the first power and NO3 to the first power. In addition, the NO2 and NO3 could continue on to react to produce an NO2, an O2, and an NO via the third reaction. Again, this would be virtually identical to step B, with the exception that the rate constant is now Kb. And the fourth reaction is an NO reacting with N2O5, producing 3 NO2s. So its rate law will also be second order, but with respect to NO and N2O5. So let's go on to step 3, essentially. What are the intermediates of this reaction, and can we apply the steady state approximation to them? So let's highlight the intermediates. So if we look in this, so what doesn't occur in both sides, we're going to assume the intermediates are going to be NO3, for example, here, 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 and that's where NO3 occurs. And we'll change colors, and let's highlight where NO would occur. NO occurs really only here and here. We are not going to consider oxygen as an intermediate because it's part of the products, and N2O5 and NO2 are either reactants or products as well. So if we continue on with the steady state approximation, what we're going to do then is say that the change of NO with respect to time is going to equal 0, and we need to ask, what is it that can change the quantity NO, or I should say which rates will change the quantity of NO. So we see from our highlight above, VB will increase NO, so I'll write plus VB, and VC will decrease NO, so I'll write minus VC. Since this is equal to 0, we can say that VB equals VC. Therefore, the two rates will equal each other, and essentially we can copy the VB rate information, and we can copy the other rate and see that those are equal to each other. So let's take that equation and solve for NO. So in this case, concentration of NO is going to equal Kb B NO2 NO3 divided by Kc and then N2O5. So note that we have, in this case, solved for NO, but we still have the NO3 intermediate as a concentration that participates. We don't know what that is yet. So now let's apply the steady state approximation of NO, the steady state approximation to NO3. So to keep in parallel with that, dNO3, that rate, is going to, I'm just going to add the approximate sign to the one above, so the dNO3 dt, if we apply the steady state approximation, and I'll just say SSA here and SSA, so we highlight the need to use the steady state approximation. So what can change the concentration of NO3? If we go back up and look in the pink, we see that VA will increase the concentration, VB, I should say VA minus will decrease the concentration, and VB will decrease the concentration. So what we can do then is substitute the values for, or relationships for VA, VA prime, and VB into that equation, and solve that for NO3 and see if we can solve that uniquely without having other intermediates in it. So this will equal VA, which is equal to Ka, concentration of N2O5, minus, I'm just going to slide this up and move it over so I can write a little easier, minus Ka prime, bracket, NO2, and then NO3, and then I'll write below minus Kb, NO2, and NO3, and this has to equal 0. So let's just take a look to make sure we got everything correctly. That's going to be Ka, N2O5 minus Ka prime NO2 times NO3 minus Kb NO2 NO3. If we're going, we can then take and solve this for NO3, and it turns out then that excuse me, concentration of NO3 is going to equal Ka times the concentration of N2O5 divided by the sum of Ka prime plus Kb times concentration of NO2. So in this case, we have the ability to take the concentration of NO2 and bring it up and put it into this equation and remove the NO3 variable from the NO equation. So let's say that this is going to equal, now I'll repeat this, Kb NO2 over Kc N2O5, and then replace NO3 with our expression from below, Ka N2O5 divided by the sum of Ka prime plus Kb and divided by NO2. So what do we notice here? Surprisingly, perhaps surprisingly, we see that, let's change colors, NO2 will cancel with NO2, NO2O5 will cancel with NO2O5, and we're left with now a collection essentially of rate constants. And I'm just going to say, put this back in blue and say this is equal to, it'll be Ka, Kb divided by Kc times the sum of Ka prime plus Kb. And that's what NO on the left-hand side equals. So now we have expression for NO and NO3 that doesn't depend on intermediates. Okay, now let's focus on essentially describing a reaction rate relative to the overall reaction. And so let's go back up here and let's choose N2O5. How does N2O5 change as a function of time? And let's highlight those areas, and I'll use purple, I guess. N2O5 shows up here, N2O5 shows up here, and N2O5 shows up there. So we need to have three terms in our expression for how N2O5 is going to change. So let's go ahead and put that down below. So I'm going to say dN2O5 dt is going to be decreased by reaction A, increased by reaction A prime, and decreased by reaction C. So down here I'll say VA is going to be negative, VA prime is going to be positive, and VC is going to be negative. Now what we need to do is see if we can simplify this before we start putting in expressions for VA, VA prime, and VC. And if we look up above, and I'll continue with the highlighting in purple, notice this equation. That has a unique relationship that looks very close to what we're talking about already, as well as the VB equals VC. So what we notice is that we can use those together. And so if I start out over here, I can say minus VA plus VA prime plus VB is going to equal 0, because we know that from the steady state approximation. And we know that VB equals VC, so that we can end up with negative VA plus VA prime equals negative VB, which has to equal negative VC. So over here we can say that this piece can be replaced with minus VC plus a minus VC, meaning that equals minus 2 VC. And if we go up, we can use the definition for what VC is. And down here we'll say then that dN2O5 dt equals minus 2 times VC. And so let's put that in. That is Kc, concentration of NO, times N2O5. But we do have an expression for NO, and that expression up here is Ka, Kb divided by Kc, and then divided by the sum of those two values. So let's put that in here. That's going to equal negative 2 Kc, and that'll be Ka, Kb divided by Kc times the sum of Ka prime plus Kb times, we have to not forget the NO2 or N2O5. And so if I highlight this portion, that is coming from NO as the intermediate. So what do we notice? And actually that color is virtually impossible to see. We see that Kc will cancel, and we're going to be left with an expression for the change in N2O5 dt equaling minus 2 Ka Kb N2O5 divided by the sum Ka prime plus Kb. And there we have an expression for the rate law using the steady state approximation on our intermediates